For decades, physicists built a model of the edge of our solar system so detailed, so carefully calculated, that they were confident they knew exactly what a spacecraft would find the moment it crossed that boundary. A sharp line. A clean handoff. The sun's influence ending, the galaxy's beginning, marked by a magnetic field that would visibly, unmistakably change direction. Then a spacecraft actually got there. And the magnetic field didn't change direction at all, not by a small margin, not within the noise of the instruments. It simply stayed the same, as if the boundary between our solar system and interstellar space wasn't a boundary in the way anyone had modeled it. And when a second spacecraft crossed that same line 6 years later, from a completely different angle, it found the exact same thing. 2 independent machines, 2 separate crossings. One result that, according to the physics everyone trusted, should not have been possible. This is the story of what Voyager 1 actually found at the edge of the solar system, why NASA scientists are still working through the implications of it, and what it means for the invisible shield that protects every living thing on Earth. Let's set the stage first, because the setup matters as much as the discovery. Voyager 1 launched on September 5th, 1977, on a mission originally expected to last about 5 years, a flyby of Jupiter, a flyby of Saturn, and then a slow fade into silence. Instead, it kept going, using the gravity of each planet to slingshot itself farther and faster than any spacecraft before it, sending back the first close-up images of Jupiter's storms and Saturn's rings along the way. By the time the 1980s ended, it had already become the most distant human-made object ever launched, and it never stopped moving, never stopped transmitting. The sun doesn't just sit quietly at the center of the solar system. It constantly blasts out a stream of charged particles called the solar wind, and that wind inflates a vast bubble around everything we know. Every planet, every moon, every spacecraft we've ever launched. And that bubble is called the heliosphere. Its outer edge, the point where the pressure of the solar wind finally gives way to the pressure of the interstellar medium pushing back from outside, is called the heliopause. For years before any spacecraft reached it, scientists built detailed simulations predicting what that crossing would look like. Because the sun's magnetic field and the galaxy's magnetic field come from entirely different sources and point in different directions, the models were confident that the moment a spacecraft crossed the heliopause, its instruments would detect a dramatic rotation in magnetic field direction. Solar influence ending here, interstellar, influence beginning there, a clean and measurable handoff. On August 25th, 2012, Voyager 1 crossed that boundary. It was already 35 years into a mission originally planned to last 5. Its instruments detected the solar wind particles collapsing to almost nothing. They detected a sharp jump in the density of surrounding particles. Every sign pointed to the same conclusion. Voyager 1 had left the solar system and entered the space between stars, becoming the first human-made object in history to do so. But the magnetic field reading didn't match the model. It barely changed at all. At first, scientists assumed it had to be some kind of temporary anomaly, a local fluctuation, a fluke of timing, something that would resolve itself as Voyager 1 continued deeper into interstellar space. So they kept watching. And it didn't resolve. 3 years later, with the spacecraft nearly 16 astronomical units past the boundary, the magnetic field was still holding the same orientation and the same strength it had shown at the crossing itself. Researchers formally ruled out the idea that this was some kind of short-lived instability. It wasn't temporary. It was simply how that region of space actually behaves. Then, on November 5th, 2018, Voyager 1's twin, Voyager 2, crossed its own heliopause boundary on a completely different trajectory, at a different point in the sun's activity cycle, years after its sibling. If the first result had been some strange coincidence tied to Voyager 1's specific location or timing, Voyager 2 should have found something different. It found almost exactly the same thing. The magnetic field, once again, failed to rotate the way the models predicted. And even more strikingly, Voyager 2 crossed the heliopause at a distance of roughly 119 astronomical units from the Sun, nearly identical to where Voyager 1 had crossed 6 years earlier, despite the solar wind being in a completely different state at the time. 2 spacecraft, 2 different eras of solar activity, converging on nearly the same boundary distance and the same impossible magnetic field behavior. There was another detail buried in the data that made the picture even stranger. When researchers measured the actual strength of the magnetic field at the crossing, not just its direction, Voyager 1 recorded a value roughly twice as strong as theoretical models had predicted for that region. That's not a rounding error. That's a fundamental mismatch between what decades of magneto-hydrodynamic simulations said should be there and what the instrument actually measured. Sitting in the one place, no simulation could ever fully substitute for. One physicist involved in analyzing the data, Stamatios Krimigas, later put it about as plainly as a scientist ever does. Nature, in this case, simply hadn't read the theorist's papers. So what's actually going on? If the magnetic field isn't behaving the way the models demanded, what does that tell us? The leading explanation involves something called magnetic reconnection, a process where magnetic field lines from two different sources, in this case the sun's field and the galaxy's field, don't simply meet and separate cleanly. Instead, they tangle, stretch, and partially merge with each other, releasing energy in the process and effectively blurring what should have been a sharp boundary into something far more gradual and interconnected. Rather than the sun's magnetic domain ending abruptly at the heliopause, the data suggests our solar system's magnetic influence is, in a very real sense, threading into interstellar space itself, and vice versa. That reconnection process appears to explain another discovery that came alongside it, one that earned its own nickname among researchers studying the data, the Wall of Fire. As Voyager 1 and later Voyager 2 approached and crossed the heliopause, their instruments recorded plasma temperatures in the range of 30,000 to 50,000 Kelvin, several times hotter than the surface of the sun itself, in a region of space that earlier models had generally expected to be cold and comparatively calm. Researchers studying the data have since described it as a patchwork of hot and cold zones rather than a single uniform boundary, with charged particles becoming trapped and compressed in some pockets and creating pronounced spikes in temperature, while nearby regions remained far cooler, producing an uneven, layered structure that earned the nickname the Wall of Fire among the scientists tracking it. To be clear, this isn't heat in the way we experience it. The particles in that region are so sparse and colliding so rarely that despite carrying enormous kinetic energy, there was nothing dense enough to transfer damaging heat to the spacecraft itself. It's a genuine temperature reading, in the true physical sense, produced by charged particles moving at tremendous speeds and colliding infrequently in an almost empty stretch of space, likely energized by the same magnetic reconnection compressing and heating the plasma right at the boundary. Put together, these two findings, a magnetic field that refuses to rotate the way theory demanded, and a boundary running dramatically hotter than expected, both confirmed independently by two separate spacecraft years apart, paint a picture of the edge of our solar system as something far messier, more dynamic, and more interconnected with the wider galaxy than any model built before Voyager got there ever assumed. Some researchers have gone as far as describing the heliopause, not as a wall at all, but as a genuinely active, breathing interface, one where the sun's influence and the galaxy's influence overlap and interact, rather than simply meeting and stopping. And this isn't just an interesting footnote about a distant boundary nobody will ever visit. The heliosphere is the shield that stands between Earth and the harshest cosmic radiation drifting through the galaxy. High-energy particles that could otherwise reach the inner solar system, including our own planet, at much greater intensity. If the boundary of that shield behaves in ways current models can't fully explain, if it's more porous, more turbulent, and more magnetically connected to interstellar space than we assumed, then understanding exactly how that shield holds up over long timescales becomes a more urgent and more complicated question than it looked a decade ago. It's worth pausing on why that question is so hard to answer from Earth alone. Every model of the heliosphere built before Voyager reached it was constructed the same way. From telescopes pointed outward, from theoretical simulations run on computers, from indirect measurements taken from deep inside the bubble itself. None of that is a substitute for an instrument physically present at the boundary, recording what's actually there rather than what physics says should be there. That's the entire reason this finding carries so much weight. It isn't a refinement of an existing theory. It's a direct, repeated physical contradiction of, one, measured twice by two separate machines under two different conditions. This is precisely why the aging Voyager spacecraft still matter so much right now, in 2026. They remain the only instruments humanity has ever placed directly inside this region, and every additional year of data they send back is additional evidence bearing on a genuinely unresolved question in physics. Both spacecraft are extremely limited today. Voyager 1 is currently running on a fraction of its original power, with several of its instruments already switched off permanently to conserve what little electricity remains, and NASA engineers have spent this year testing experimental procedures just to keep its dwindling systems alive a little longer. In just a few months, on November 18th, 2026, the Voyager 1 will cross one light day from Earth, a distance so vast that a signal moving at the speed of light takes a full 24 hours just to arrive, a reminder of exactly how far this small, aging machine has carried our only working theory of the galaxy's edge and how much farther it might still have to teach us before its power finally runs out. Eventually, both spacecraft will run out of power completely, likely sometime in the early 2030s. When that happens, the only real-time, in-place measurements of this magnetically tangled, unexpectedly hot boundary will stop. No replacement mission currently exists that could reach the same region in anything less than several decades. Whatever remains unresolved about why the magnetic field refuses to rotate, and exactly what mechanism is heating that boundary so intensely, may stay unresolved for a very long time after Voyager finally goes quiet. For now, though, the finding stands, confirmed twice independently by two different spacecraft separated by years and by an entirely different phase of the Sun's activity. The edge of our solar system isn't the clean, orderly line the models confidently predicted. It's tangled, energetic, and still not fully explained, and the only reason we know that at all is because two small, aging machines built in the 1970s kept transmitting long enough to prove the theorists wrong. There's something worth sitting with in that fact alone. Every prediction about the heliopause, right up until the moment Voyager 1 actually crossed it, came from brilliant physicists working entirely from indirect evidence, doing the best science possible with the tools available to them. They weren't wrong because they were careless. They were wrong because no model, no matter how carefully built, can fully substitute for a direct measurement taken from inside the thing you're trying to describe. That's the quiet lesson sitting underneath this entire discovery, and it's one that will likely keep repeating itself the deeper humanity eventually manages to go. If you want to see what Voyager reports next as it pushes past one light day from Earth, subscribe and turn on notifications, because the spacecraft that already broke one model of the universe may not be finished breaking others.